This is Darrell presenting Apple's Develop in Swift Data Collections Curriculum, Unit 2, Lesson 1, Closures. This is advanced material, but we need to be able to call APIs that take closures as arguments. In SwiftUI, we are using closures all the time. Closures are very flexible. We can write a function such as sorted, where we pass in a closure, which is a set of code that identifies and determines how the sort works. So that way we can use an advanced and efficient sorting algorithm where the comparison is based on our code. At the top, we have a function. Functions have a name, they have parameters or may have parameters, they may have return types, and then they have code. Here's the related closure. In this case, we've given the closure a name and set it equal to a set of code. That code has parameters, that code has a return type, and then we use the in keyword to separate the parameters and the return type from the code which actually executes the closure. Here are 4 examples of closures. In the first one, we have no parameters and we do not have a return, we do not return anything, and then we have our code that executes. In the second one, we have one parameter, which is of type string. We do not have a return value, and then we have our code. In the third one, we have no parameters. We have an integer return type, and then after the in keyword, we have our code. And then in the fourth example, we have 2 parameters. We have a return type. We have our keyword in, which separates that from the code, and then we have our code. Functions can take closures as arguments. Here's an example, the sorted function. The sorted function has one parameter, which could be implemented as a closure. And so rather than passing it a comparison function, we're passing it a closure which has the comparison code in it. That comparison code takes 2 arguments and it returns a Boolean, which is true or false. And that indicates whether the first argument or the second argument should come first. Here's the second example of sorted, where we pass it a closure, which again has 2 arguments, and it returns a Boolean indicating whether the first argument or the second argument should come first. Here's the second closure from the prior slide. This closure is sorting based on the star rating as opposed to the name of the track. That's what passing a closure to sorted lets us do. We can sort based on any parameter or any algorithm associated with our data structure. The syntax for a closure is a little complex, and we would like to be able to simplify it, and the compiler helps us do that. Tracks is a collection of track. So the compiler knows that the sorted method is going to send 2 tracks as 2 parameters to the closure. So we don't need to specify the type of the parameters as track because the compiler knows that. So we can remove that. The compiler also knows that sorted is expecting whatever closure we pass it to return a Boolean, so we can remove the returns Boolean from our closure definition. The compiler will infer that. If we want, rather than having names of our parameters, we can replace them with $0 and $1 and so on. So the first parameter would be $0 and the second parameter would be $1, and then we can access them the same way inside the code. And we don't actually need our parameter list because the compiler knows that the sorted method is going to send 2 parameters to whatever closure is there, so it knows that the closure has to have 2 parameters. We also removed the in keyword because we didn't need to separate any parameters anymore from the code. Now our code only has 1 line with 1 statement. And if you have a function or a method with 1 line, then you don't even need the return keyword. This is the final distilled version. The sorted method sends 2 tracks to our closure. And so we sort the two parameters based on their star rating and return true or false depending on whether the first parameter comes before the second parameter. We've eliminated a lot of boilerplate code, and as a result, our sorted method is easy to call. We could also pass a function if the function signature matches what is required of the closure signature. For example, the less than function takes two parameters and returns true or false based on whether the first parameter comes before the second parameter. We usually implement the less than function when we make a data structure conform to the comparable protocol. So if tracks conformed to the comparable protocol and had a less than function, then we could just put the less than function in our tracks.sorted argument. Or if we prefer to compare by a custom algorithm, then we would use a closure with a custom algorithm, or even another function that also had a matching signature, again taking two tracks and returning a Boolean. Swift collections have methods that use closures. Map will return a new collection by applying the closure that you passed to each item in the existing collection. Filter will return a new collection filtered by a closure, where the closure returns true or false to determine whether the new collection should be in there. Reduce uses a closure to convert a collection into a single value. Here we have an array of first names, and we want to create an array of full names where each name has the same last name, Smith. So for each name in our first names array, we let the full name equal the first name plus space Smith, and then we append that full name to our full names array. Here's an alternative implementation where we take our collection and then we map it with a closure. And the closure will take each name and return a string. And when it returns a string, the string that it returns will be the original first name plus space Smith. The .map will take our existing collection and make a new collection executing this closure on each element. So as a result, we will end up with a full names array where it is Johnny Smith, Nellie Smith, Aaron Smith, and Rachel Smith. Map does the iterating for us. Here we use the syntactic sugar to make our closure easier to write. The first thing we do is change the parameter to $0. So we don't need the parameter name and we don't need the in keyword anymore. The second thing is our return type. We know the compiler can infer that the return type is string, so we don't need to specify that we're returning a type of string. And as a result, our closure is easier to write and read. Here we have an array of numbers, and we have a new array of integers, and we iterate through our array, and for each integer in our source array, if it is less than 20, then we append it to our destination array. Here's how we can do the same thing using the filter method. We filter, and filter takes each integer in our source array and returns a Boolean, and in our case we're returning true if the integer is less than 20, and then filter will create a new array based on the old array, but only including the elements that pass the less than 20 test. Here we've used our syntactic sugar to make the closure as simple as possible. The parameter name, it had one parameter, so we just call it $0. We know the return, we can infer that the return type is Boolean because filter expects a type of Boolean, so we don't need the return type. That means we don't need the in keyword anymore. It is only one line, so we don't need the return keyword. So our filter is just, is our parameter less than 20? As you can see, this closure is easy to read, and we know exactly how we're filtering our source array into our destination array. Here we have an array of integers, and we want to calculate a total. So we iterate through the array and add up each integer in our source array to result in a total. Here we're using the reduce method to calculate our total. we give it an initial value, and then for each iteration of the array, we have the current total, and then we have the new value which comes from our array. And it returns the same type that was our array. In this case, our array was integer, so our initial value has to be of type integer, and our return value for each iteration for the closure is integer. And then we have our code to calculate the new output value, which is just adding up the initial value with our new value to generate a subtotal. When after the reduce method will execute this for each number in our array, resulting in a grand total. Here we've used the closure syntactic sugar to simplify our closure as much as possible. The first argument of reduce is the initial value, which has to be the same type as our array, and so we've included an initial value of 0. The second argument for reduce is our closure, where in this case we have two parameters in our closure, the current subtotal, which started out as the initial value, and then the new element. So for each iteration, we're adding our subtotal, we're adding our new element to our current subtotal, and then that results in a grand total. So the reduce method will end up resulting in one integer. So unlike the other collection functions, the reduce collection function takes an array of integers or an array of some item and results in one item, which is based on all of them using our algorithm. You might notice that our syntax is a little bit different here. We are not using what's called trailing closure syntax. If a function's last argument is a closure, then you could put the parenthesis one element earlier and then have the closure. In this case, we're keeping the parentheses around both of our arguments, and so the closure is inside the second parameter to the reduce method. Either way is valid. They're syntactically equivalent. If we had a function that matched the signature of reduce's closure parameter, then we could simply pass in that function. In this case, our array is of type integer, so our function needs to take two parameters of type integer and return one parameter of type integer. So the plus function does that. It takes two numbers, or two integers in this case, and returns an integer. So rather than having an entire closure, we can just put the plus function here. Likewise, we could put the minus function or a multiply function, because those also take two integers and result in one integer, so their signatures match. Closures capture their environment. So here we're executing an animate method, and we're passing it a closure, and so the animate method might occur over the next couple of seconds as the animation is executed. However, inside the closure, we can still access properties that were in scope when we activated the closure. So we can still access self.view.background color and assign it. If you are following the Apple curriculum, now is the time to open the Closures Playground and complete those in the lab. This slide deck is copyright by Apple and is licensed by Apple under the Creative Commons Attribution Non-Commercial Share-alike 4.0 International License.